Railroads around the world follow one invisible rule. A single axle can only press a limited weight onto the rails. In North America, that limit is roughly 70,000 pounds per axle. That number exists for a reason. Exceed it, and rails can bend, bridges can crack, and the ground beneath the tracks can shift. For over a century, engineers designed rail networks around this boundary. But modern industry created a problem no one expected. The machines that power our world kept getting bigger. Massive power transformers, generators, and nuclear reactor vessels now weigh over 1 million pounds. That's more than 10 times the weight of a normal freight car. Moving something that heavy across a railroad isn't just difficult, it's almost impossible. Think about the math. A standard freight car has 4 axles. If you placed a 1 million pound transformer on top of it, each axle would carry over 250,000 pounds, more than 3 times the safe limit. That would destroy bridges, warp rails, and possibly derail the train. Yet these enormous machines must still travel across continents. They power cities. They support power grids. They are critical infrastructure. So the question becomes, how do you move a 1 million pound object across a rail system designed for far lighter loads? The answer is one of the most brilliant engineering solutions in railway history. A machine called the Schnabel Car. Instead of carrying the load, it becomes part of the train itself. And that changes everything. For 2 minutes video, the secret behind the Schnabel Car is surprisingly simple. Distribute the weight. Instead of placing a massive transformer on top of a railcar, engineers designed a system that clamps the cargo between 2 enormous lifting arms. The cargo itself becomes a structural beam, connecting both halves of the train. This design comes from the German word Schnabel, meaning beak. Like a giant mechanical bird, the arms reach out and grip the cargo from both ends. Now the impossible math suddenly works. Imagine a 1.1 million pound load, including the transformer and the railcar. Instead of 4 axles, the Schnabel car spreads the weight across 36 axles. That means each axle carries only about 30,500 pounds, less than half the maximum allowed weight on North American railways. The force is no longer concentrated. It's distributed across dozens of wheels, like a bridge spreading weight across multiple supports. But weight distribution is only part of the story. Schnabel cars also include powerful hydraulic systems. These systems allow operators to lift the load up to 44 inches above the rails, shift it sideways up to 40 inches. Why does that matter? Because railways are full of obstacles. Signals, platforms, bridges, tunnels. Sometimes the clearance is just a few inches. Sensors constantly measure the weight distribution on every clamp and axle. If the balance shifts by more than 2%, alarms sound and the train stops immediately. It's not brute force. It's precision engineering controlling one of the heaviest objects ever moved on rails. Even with a Schnabel car, moving a 1 million pound load is never simple. Speed becomes the next challenge. When a train moves, forces increase due to vibration and motion. Engineers call this the dynamic amplification factor. At 25 miles per hour, the effective weight on each axle can increase by about 15%. A load that weighs 40,000 pounds per axle at rest can feel like 46,000 pounds while moving, still within limits, but much closer to danger. That's why Schnabel trains usually travel between 15 and 25 mph, and sometimes even slower. Before the journey begins, planners spend 6 months or more preparing the route. They analyze bridge strength ratings, track conditions, tunnel clearances, signal locations. Every inch of the route is measured with laser surveys. Insurance coverage for a single move can exceed 500 million. And fewer than 100 Schnabel cars exist in the entire world. When the train finally begins its journey, the crew constantly monitors the load. Imagine a moment like this. A 1.34 million pound generator approaches a bridge rated for 1.2 million pounds. The train slows to 5 mph. Hydraulic operators carefully adjust the load, shifting it by fractions of an inch, balancing the weight across 36 axles. The crossing takes nearly 3 minutes. Every crew member watches the sensors. Every number matters. Then the final axle clears the bridge. The structure holds, and the train continues. A quiet reminder that modern infrastructure doesn't rely on brute strength.